In this video, we'll discuss Gaussian elimination and Gauss-Jordan elimination. Now, when we talk about these two, we are talking about solving systems of equations using augmented matrices. Both of them will use elementary row operations to simplify the matrix. This includes replacement, where we can replace a row by the sum of itself and a multiple of another row. We can interchange rows, and we can scale a row. Now, the difference between the Gaussian and Gauss-Jordan elimination is that Gaussian elimination stops at row echelon form, whereas Gauss-Jordan uses reduced row echelon form. So you might ask yourself, well, what does that mean? When we talk about row echelon form, we're talking about that if there's a single row of all zeros, that goes to the bottom of the matrix. For all other rows, the leading entry will be a 1. And it should be in the top left and then going diagonally to the bottom right. But if you see in the row echelon form, there can be other numbers inside of a row after that leading coefficient. What happens then is we have to go back and back substitute to find the rest of the solutions. So typically you'll have a single solution at the bottom and you'll work your way up the rows then solving those equations. In contrast, the row reduced or the Gauss-Jordan elimination will take it and make the identity matrix on the left-hand side of the augmented matrix, which then shows what each solution is for each of your variables. So it's another way of simplifying it all the way down without having to do that back substitution. Both methods work perfectly fine. It's just a matter of how far do you want to go with your simplification of the matrix. So let's look at an example. Say we have 2x1 minus 2x2 equals negative 2, x1 plus 6x2 plus x3 equals 28, and negative x1 minus 4x2 plus 8x3 equals negative 11. And we want to solve this system to find each of those variables. So first thing we have to do is put that in a matrix. And if we look, that would become 2, negative 2. We put a 0 because there is no x3 in the first equation. And then for the augmented portion, negative 2 is the solution. Then it goes 1, 6, 1, 28. And then we have negative 1, negative 4, 8, and negative 11. Now we want to start reducing our rows. And you can see here, we're going to do a row reduction. And we're going to substitute the second row by multiplying the first row by negative 1/2 and adding that to row 2. So we're going to do half of row 1 subtracted from row 2. And that would give us then 0, 7, 1, 29. Now we want to remove this bottom term, negative 1. So we're going to then say, we're going to take row 3 and add half of row 1, since that's already negative. And if I do that, I'm down to having a 0, negative 5, 8, negative 12. So we've now turned it so that our first column has just one leading coefficient. It's not simplified, but it is there. Now what we can do is we want to say, okay, we want to get rid of the negative 5 so that the 7 becomes a leading coefficient in the second row. So we're going to multiply this row by 5. We're going to multiply row 2 by 5/7 and add it to row 3, which gives us 61/7 and 61/7. Now we can go through and then say, okay, let's simplify that because that's a little hard to work with. So we're going to multiply that third row, just do a scaling operation by 7/61, and what that will create then is the third row being 0, 0, 1, 1. Now, if we're in Gaussian elimination, that's all we need to do. We've got it to a point where we have one of our variables, and we can then back substitute up through the matrix. So we can say we know x3 is 1. So let's go back to the second row. We know that 7x2 plus 1, because it's 1 times 1, will equal 29. We solve that basic two-step equation and we get that x2 is 4. Now we have both x2 and x3. We can take it back to our first row and say now we have 2 times x1 minus 2 times 4, and you could say plus 0 if you want, but you don't have to, equals negative 2. I simplify, so it's 2x1 minus 8 equals negative 2. So 2x1 equals 6, therefore x equals 3. So we can say that the solution to this system would be 3, 4, and 1. Now, say instead we want to go the Gauss-Jordan elimination method. we would stay where we are, but we keep going. We wouldn't do that back substitution. We'd work on the matrix itself and say, how can we simplify this matrix? So the first thing we would do is we would take the second row and subtract the third row so that we can get that third column with all zeros and that 1 in the third row. So that would give us then in the second row 0, 7, 0, 28. Now, remember the idea is that we want to have our leading coefficient as 1, and then it'd be zeros making that identity matrix, and then the augmented portion. So we'd say 1/7 of row 2. That'll get us to where we're part of that identity matrix where it's 1 and 4. Now we need to simplify our first row. So we're going to take, and we need to remove this -2, so we can say half of row 1, because that will turn our 2 into 1, plus row 2, and that should give us our identity matrix on the left side, and then our solutions on the right side of the augmented matrix. And when we do that, we'd end up with the identity matrix there, and then 3, 4, 1, therefore also showing the solution of 3, 4, 1. So whether we use Gaussian elimination or Gauss-Jordan elimination, we will end up with the same solution.